its design and implementation of a very short retention time filtrate clarifier. I would like to thank the members of my committee for being part of this project and for their advice. The presentation will be divided in five sessions. First, I will give you the motivations for developing a very short retention time filtrate clarifier. Then I will describe the process and give some design concepts that we use to develop the project. I will talk about the results that we obtained during the 2012 Louisiana harvest season when we tested this unit. And I will also introduce to you a new design that will be built in the new LLT clarifiers. Finally, conclusions. Let's start by explaining a little bit of the sugarcane process. And it all starts when the cane arrives to the mill and it's crushed in the mill, and the juice is extracted. This juice then is limed to start the formation of small flocks, and it's heated superheated above its boiling temperature to be able to degas it in an external flash tank. This allows all the dissolved air in the juice to be removed and enhances the performance of the clarifier. After this operation, a small dose of flocculant is added to the juice, and it arrives to the clarifier where two phases are obtained. A clear juice that is sent to other steps of the operation, and a solid mud phase, which still has a lot of recoverable sugar. Therefore, it's sent to vacuum filters where a filter cake is obtained and it's discarded from the process. And a filtrate, which accounts for almost 15 to 20% of the total juice, and its quality is very low compared to the clear juice that is sent to the other steps of the process. Therefore, it is usually recirculated, being detrimental to the process. Some of the disadvantages this recirculation brings to the operation are: it reduces the clarification throughput. It can increase sucrose losses either by promoting microbial activity or inversion of sucrose. It can lead to increased sugar color by promoting the destruction of reducing sugars. And it can also increase the turbidity difficulty in the operation of the main clarifiers because the filtrate has very light particles that are difficult to clarify. To avoid this recirculation, several alternatives have been proposed. The most popular one has been the clarification of filtrate either by flotation or settling, but there's still a lot of resistance to implement this technology because basically the reasons I found is that the studies that have been conducted were small-scale experiments that did not represent the factory conditions. Also, some of the proposed processes were very complex, requiring the addition of one or more flocculants or additional unit operations. In some cases, the quality of the clarified filtrate was very poor, or the information available, it wasn't enough to really assess the quality of this clarified filtrate. And finally, and I think it's the most important one, is the long residence times of the clarifiers utilized, which can be up to 2 hours and can lead to equivalent sucrose losses as the recirculation itself. These long residence times in the clarifiers occur because the fluid, the juice that arrives to the clarifier is highly turbulent, leading to significant internal recirculations. These recirculations can be observed when two of the most popular clarifiers used in the industry for mixed-use clarification or for filtrate is simulated with CFD. Fortunately, in the Audubon Sugar Institute, which belongs to LSU Ag Center, Dr. Vadim Kochergin and Mr. Seigel developed a juice distributor that can enhance the clarification performance. They have proposed a turbulence reduction device, which is a juice distributor that can reduce that dissipates momentum and effectively reduces the turbulent eddies present in the flow. Please observe that when there's no TRD, there are high velocities as well as huge internal recirculation. when the TRD is implemented, these velocities are reduced and the recirculations as well. This can lead to enhanced clarification and can probably lead to lower residence times. This effect can also be observed experimentally when there's no TRD when a dye test was conducted, and when there's no TRD, please observe that the dye it's poorly dispersed. Also, on the contrary, when the TRD and high turbulence can be observed in the surface. On the contrary, when the TRD is implemented, improved utilization of the settling area can be observed, as well as reduced turbulence in the surface. This can lead to improve the clarifier's performance. Therefore, knowing that this technology was available, we wanted to revisit a filtrate clarification with a whole new approach. So the goals of our project were, we wanted to develop a very short retention time filtrate clarifier to treat this filtrate and avoid its recirculation. We wanted to apply the turbulence reduction technology to the filtrate clarifiers. And we also wanted to find the best process conditions to achieve a clear filtrate with enough quality to be combined with a clear juice that is obtained in the main clarifiers. Finally, if we were successful, we wanted to complete the full cycle from the concept, implementation, to the technology transfer. The expected benefits if the very short retention time clarifier was fully operational are: we can increase the clarification capacity by 15 to 20%. We can process high throughputs of filtrate in a very small unit. We can achieve higher sucrose recovery by avoiding the recirculation that can lead to inversion. And finally, we can reduce the destruction of reducing sugars that can lead to color generation. To achieve this this idea, we follow basically 3 big steps. First, it required the design and sizing of all the process and equipment. It also required the building and commissioning a pilot plant in a sugar mill, which was Alma Plantation, and it's located close to Lakeland, Louisiana. And we also run some preliminary laboratory tests to design the protocols and also identify the critical operational parameters. Finally, we run the experimental factory trials to assess the performance of this new clarifier. The design concepts that we had in mind while developing this clarification unit was, we had to have a fully scalable clarification pilot plant that really represented the factory conditions. Therefore, we sized our pilot unit to treat up to 100 gallons per minute of filtrate. Also, we should keep the process as simple and effective as possible. And the clarifier must have a very short residence time, at least 10 minutes or less, compared to the 30 minutes or 2 hours of the other clarifiers. Finally, we wanted to test the limits of the turbulence reduction technology. Before the commissioning of the pilot plant, we run some batch sampling tests, which are some lab-scale clarification experiments to identify which was the best flocculant dose and if we require the addition of extra lime to promote the flocculation. From the experimental results, we observed that with the extra addition of lime, we could have lower turbidity, and that the best flocculant doses were 4 and 6 parts per million, achieving lower turbidity with 4 parts per million and higher settling rates with the higher dose. So we narrowed the variables to be tested in the factory trials. I'm sorry. the process that was proposed to treat the filtrate from this factory consisted in we sent part of the factory filtrate to the heat exchanger, and we heat it in one stage to above boiling point, just to slightly superheat the filtrate and be able to degas it in the external flash tank. Before, we added some lime to adjust the pH and the flocculant. Finally, all the filtrate is sent to the clarifier where the two phases are obtained, a clear filtrate and the muds. Because this was an experiment, we didn't want to affect the performance of the factory in general. So after sampling our clear filtrate, we mixed these two streams again and return it back to the operation. Some other process conditions that we had during the operation were, we designed our pilot plant to treat 100 gallons per minute. That was our goal. But due to some filter limitations, the maximum flow rate was 60 gallons per minute. Therefore, we tested an intermediate flow rate and the maximum, which was 40 and 60 gallons per minute. Also, we found that the addition of phosphoric acid was not necessary because the phosphates that appear naturally in the juice were above its recommended value. These phosphates are important because they react with the lime saccharide to form the flux. We also used one-stage heating, and we superheated our filtrate to 220 degrees Fahrenheit. And we used a hot liming technique and adjusted the pH to 7.8. The flocculant addition, as I discussed before, were 4 and 6. And with these two flow rates, the nominal residence times that we could expect in the clarifier were 12 and 8 minutes respectively, which still very low compared to the current technology. And this is the pilot plant we built in Alma. So here you can observe the heat exchanger, the flash tank, and the clarifier, which is this one. And this is an internal view of the unit where we can observe the TRD and the overflow trough where the clear juice that we obtain from the clarifier is collected at the top of the clarifier. To assess the performance of this unit, we took several measurements to the samples we collected during the operation. These were the turbidity of the juice, the phosphates concentration, the suspended solids, and juice color before and after clarification. And we also wanted to know what was the amount of losses that we could expect in this clarifier. Therefore, we calculated from experimental data the inverse to sucrose ratio, which can give us this value. The turbidity and the phosphates are relatively easy measurements to perform in the factory. Therefore, and they are necessary to assess the performance in real time of the clarifier. Therefore, they were measured on site. However, all the rest of the measurements were conducted at Audubon Sugar Institute, and to avoid its degradation, we preserved them using dry ice. And this is how the results look like. Please observe that this is the filtrate before being clarified, and you can see that the light doesn't pass through that sample. After clarification, this is the filtrate we obtained, and we have estimated that this reduction could be of the order of 83%. Also, when we compare the clear filtrate obtained in our pilot plant with the clear juice from the main clarifiers, by simple inspection, they look pretty similar. But when we compared numerically using the turbidity, we found some interesting results. First, when we compared the treatments that we tested with the flow rate and the flocculant dose, we found that in terms of turbidity, they were not significantly different, suggesting that we can operate our clarifier at very high residence times with low flocculant dose. and leading to the lowest residence time possible. Also, when we measured in every trial a batch test all the time where we were operating the filtrate, the filter power plant, and this batch setting test is the best clarification you can expect. There's no turbulence, it's just a jar. And the results show that the clear juice, the clear filtrate from the unit and the batch setting test were not significantly different, suggesting that that the clarifier achieved the expected target turbidity set by this batch setting test. Also, we compared the turbidity from the clear juice from the main clarifiers and the clear filtrate, and they showed to be significantly different. However, we simulated the mixture in a proportion of 1 to 5, which is the worst case scenario when you combine the two streams. And it showed that the target turbidity of 180 NTU units was met, suggesting that this won't affect the performance of the whole factory, while when the clear filtrate it's sent forward in the process. Now, the main objective of clarification is to remove the suspended solids. And we measured this, we made this measurement before and after clarification. Before being clarified, the filtrate had a suspended solids concentration that ranged between 6,000 to approximately 9,000 parts per million. After being clarified, we reduced this concentration to 500 to 1,000 parts per million. And we observed that the juice, the clear filtrate we obtained met the target to the suspended solids concentration to be considered a clear juice. Therefore, if we send forward this liquid to the process, we shouldn't affect the clarifier's, the clear juice quality. Now, when we compare the suspended solids removal before and after clarification, our clarifier ranged between 84 to 95%, achieving a higher removal rates at a higher flocculant dose. However, when we use that same concentration of same dose of flocculant but different flow rates, we didn't find any significance, suggesting that we can operate our clarifier at the highest, at the lowest residence time without sacrificing quality. And this is how the suspended solids look before and after clarification. And this is in a filter paper, and please note that this is significantly, well, the reduction is significantly different. Now, in color, even though the clarification operation is not aimed to reduce color, some color can be removal can be expected. And we found that before being clarified, the filtrate color ranged between 7,000 to 6,000 to 7,000 ICUMSA units. And when we compare it to the average clear values, to the average color of clear juice in Louisiana, the filtrate before being clarified met this target. After clarification, our filtrate ranged between 5,000 to 6,000 units, being below this average, and suggesting that in a full-scale implementation, we shouldn't observe any additional color transfer of the juice, of the filtrate to the clear juice. And the color removal achieved in the clarifier ranged between 15 to 20%, and it's comparable to other studies of filtrate clarification where they have used clarifiers with high residence times, and our clarifier achieved the same ranges. Now, we As I told you before, we calculated the inverse to sucrose ratio just to detect if we have either inversion of sucrose or destruction of reducing sugars. And please observe that for all the three treatments, the parameter remain invariant, suggesting that the residence time of this clarifier is so low that probably the losses were very low that couldn't even be detected. As a matter of reference, for the inversion that we can achieve in a 2 hours residence time clarifier, it can be of the order of 0.21 grams per 100 grams of sucrose, okay? For this clarifier, we have estimated that the inversion losses could be of 0.001 grams per 100 grams of sucrose, being significantly different. And from summarizing, all these results suggest that the clear filtrate obtained in our pilot plant can be sent forward without a risk, without affecting the performance of the clarifier, and avoiding these recirculations. Now, I would like to slightly change the topic of my presentation, because during the development of this project, we devised a new idea. And basically, it consists in a clarifier with a built-in flash trough. Instead of using an external unit, we will provide the new LLT clarifiers with a built-in flash trough to degas the juice. But before I continue with that, I would like to explain why is flashing important. And flashing is important because it allows all the dissolved air in the juice to escape. It also ensures that the juice entering to the clarifier is always at constant temperature. This leads that we can improve the settling rates in the clarifier, and we can reduce the presence of some eddy currents that can occur in the clarifier. Unfortunately, in several mills in Louisiana and around the world, this is the operation that is most often overlooked. And as a consequence, you can observe presence of fiber in the clear juice. Therefore, we came with a new idea, which is this flash trough, and this will be built in the clarifier. Basically, the new device consists in pumping the overheated filtrate or mixed use to the unit, where it will be degassed in this degassing chamber. And the air or dissolved air, non-condensable gases, will be removed through these standpipes. After this operation, it will be distributed to the turbulence reduction devices and separated in the clarifier. The benefits of this new invention is that it can provide more degassing area compared to external flash tanks. It can reduce the risk of air re-entrainment, which can make float a part of the mud instead of settling. And it can reduce the cost of construction and reduce the factory footprints. This prototype was tested in a full-scale, full-scale implemented in India, in Andhra Sugars, with a 30 minutes residence time LLT clarifier. And this is how the juice looks like. Quantitatively, the results we obtained were very interesting. First, in terms of color removal, our new LLT clarifier with built-in flash trough can provide from 25 to 32% color removal, which is within the ranges expected for mixed-use clarification. Also, in the Andhra Sugars, they have a target color of 14,000 units, and the clarifier, the prototype, achieved this target all the time, suggesting that the unit is fully functional. Now, in terms of turbidity, which they measure at 420, the turbidity removal achieved in our clarifier range between 90.5 to 94.5, and the clear juice turbidity was close to the target of 3,000 turbidity units. That is the expected turbidity values for Louisiana. This also proves that the unit is fully functional and can be implemented in Louisiana, solving many of the flashing problems that have been reported in the industry. I would like to finish my presentation by giving some final thoughts. I would like to say that a very short retention time clarifier that operates under 10 minutes residence time has been developed and tested for filtrate clarification. This clarifier achieves all the clarification targets, and the clear juice can be mixed with the clear filtrate can be mixed with the clear juice. In a full-scale application, the very short retention time clarifier can eliminate this recirculation, which is detrimental to the process. Now, the Louisiana Low Turbulence technology was utilized and enabled the very short retention time clarifier to achieve significantly lower retention times compared to other clarifiers. And a patent-pending LLT clarifier with built-in flash trough has been designed and tested in Andhra sugars. The results met all the clarification targets and provided clear juice with high quality. This new design will provide more degassing area and eliminate the flashing problems experienced in several sugar factories. The TRD technology and the flash trough technology have been licensed by a company that sells clarifiers around the world. This company is Crampian International, and in a joint work with them and Audubon Sugar and a mill from Louisiana, we are working on a full-scale LLT clarifier with built-in flash trough that is scheduled to be in operation during this season. And we are also working in other project, which is a filtrate clarification pilot plant of 150 gallons capacity that will be also in operation during this season. But the difference is that we won't recirculate the clarified filtrate, but send it forward and mix it with a clear juice. And this very short retention time clarifier will come with a built-in flash trough. Finally, I would like to acknowledge a lot of people who participated in this project, and without their help, it wouldn't have been possible. I would like to thank the American Sugarcane League for partial funding of the project, Mr. George Schaefer and Crampian International for all their help and believing in the filter clarification project.